Hey guys, welcome back to our next lesson. Our lesson today is on constant differences. So we've learned about difference tables, and when we say constant, remember the word constant in general means that something stays the same. So what we're saying is, we're focusing on difference tables that have the difference be the same, so the same number the whole time. All right? Our mindset message for today is everyone's ideas are important. It's really easy to kind of fall into the trap of thinking like, oh, I belong in this math circle, or I don't belong in this math circle, and maybe even school has taught you that, but I want you guys to remember that every single person has a part to play, a role to play in math, and that's totally true. If you look at professional mathematicians, they are people who are so widely experienced, even with their growing up. Some of them, even Einstein is famous that he didn't do very well in school in general, but even especially in math and science, but he was just a different kind of learner. And so a lot of us have been trained or feel bad about ourselves, or that we don't have a part to play, but we really, really do. So it's important you remember that for yourself. Anyway, so learning goals today are essentially we're learning to determine whether a linear function matches a table. Okay? And our prior knowledge would be writing recursive and closed form rules, and of course making a difference table, because that's useful in helping us to achieve this goal right here. Okay? So let's go ahead and dive in with an example of two warm-up problems, I guess, for you to do yourselves. Okay? So here's a table given, and I'm telling you that the differences are constant. Okay? So first of all, finish the table, and once you're finished filling in the table, then I want you to write a recursive and closed form rule for the table. So you can go ahead and pause right now, and then work on those two, and then we'll come back together and look at them together. Alright, so let's tackle this together. There's lots of ways you could figure this out, to be honest with you. So all I can do right now is maybe kind of think about how I would think about filling this table out. You'll notice we're missing some things in between, but we are told that the differences are constant, right? So maybe it's helpful to actually just make a third column here and think about the difference table. The problem right now is we still don't quite know exactly what goes in there, but we have some ways we could kind of be creative and think about how to figure that out, right? You may kind of think, well, how many jumps are there? I guess I could use question marks or whatever. From 2, the only thing I know is 2 and 11, right? So from here, how many jumps does 2 make to make 11? You could think about it like that. I also like to think of it this way. From 2 to 11, how far did we travel? From 2 to 11, right? What's the difference there between those? Oh, well, that went up 9, right? Well, if I went up 3 jumps to go 9, how do we split that equally? Aha! It seems like, since this has to be 9 and there's 3 jumps, then each one of those has to be 3, right? So however you thought about that, this would be the correct differences. So that means we're just adding 3 each time. So this would be 5, 8, plus 3 is 11. Good, we're correct. And then this would be another 3 if I wanted to finish this and make that 14. So whatever method or whatever you use to do that, either way, these would all be 3, 5, 8, 11, 14. Now, take a stab at number 2. If you still weren't sure about number 2, remember I encourage you to go back and look at previous notes or whatever, but let me just give you the answers for those. One quick thing though, if this was confusing you, the fact that we started at -1 isn't something that's normal, right? We're used to just starting at 0. But guess what? 0 still kind of counts as our starting point. And remember, one of the downfalls of the recursive definition is it always has to have a starting point. So like you can't go like earlier than that. You can only start somewhere and then go on from there. And just so you know, generally speaking, 0 is always going to be what we use as our starting point for a recursive. Technically, we could build it from here if I wanted, but the standard is to do this. So let's go ahead and give the answers for this. The recursive is going to be, remember our setup, like this. And we always give our starting input output first. So our starting output is 5, because that's when x is 0. So 5 if x equals 0. And, well, remember we always have f of x minus 1, right? Because remember, what we're saying is we take the previous output right? To get this output, we take the previous one plus whatever. In this case, it's 3 each time, right? So this is going to be if x is greater than 0. Okay, so check your answer for that. There's the recursive. And the closed form, kind of similarly, it's kind of built in a similar way. We typically start when the input is 0 as well. But remember, the beauty of closed form is any input actually is okay for it, but we still like to start it off whenever the input is 0. In this case, when x is 0. So the closed form, I'll just write CF for closed form. Let's check your work. Remember, it's always starting, it's when x equals 0, right? So this output of 5, and what are we adding each time? Oh, to get to 11, for example, how many 3's did I add? 2 of them. Or to get here, how many 3's did I add to the 5? 3 of them. So the input exactly matches how many of these differences we add on, right? So this would be 5 plus 3x. So remember, x represents my input, 3 represents the difference, or delta, and then this represents my starting output, okay, just as a reminder. Now let's just dive into a few more properties, and I'll actually introduce you to our first theorems that we're going to see in this course, which are... So before we introduce those theorems today, there's 2 really interesting properties. Now, these are not things you need to memorize like vocab or anything, but they're interesting, and for those of you who the visualization helps for certain things, this maybe is going to be helpful. So the up and over property for a difference table, and by the way, this is not just for constant differences. Every difference table has these 2 properties. But the up and over property is cool, and that's basically how we built the difference table. So it's just a visualization of that. So for example, if I start here at 8, if I go up and over, those 3 numbers have a relationship, right? And you could think 8 minus 5 equals 3, hence why it's called a difference table. So if you're having trouble remembering how to make the difference table sometimes, you can think up and over. That's the way, the direction that the difference goes, right? So up and over. So that's one property of difference tables. And again, regardless of if these are constant differences or whatever, that's always going to be how those differences were made. And then another property that's interesting, we actually kind of talked about this a fair bit, but we call it the hockey stick property because essentially it looks like a hockey stick when you form it. So if we were to look at like what we talked about before, remember how when we made the closed form rule? Now the up and over really goes along with recursive because remember, you're only looking at 2 outputs that are next to each other and how they connect with this difference. So that's totally goes along with the recursive type rule. And the hockey stick is more like the closed form because remember we talked about the accumulation of differences helped me figure out what that closed form rule is. So for example here, if you remember, I started at 5 and then I went over and I went down however many 3's that got me to that 14, right? So this right here kind of looks like a hockey stick. So that's just kind of a little visualization for you guys that might kind of help those 2 types of definitions stick in your mind a little bit. So without any further ado, we're going to introduce our theorems for today and do one last little mini proof, and then we'll be done with this lesson. Okay, now finally for our first theorems here in this course, can I get a drum roll? Yes, I am waiting for you to do a drum roll right now. I'm just kidding. These 2 happen to be converses of each other. If you recall from previous courses, the converse of a statement just means like you're flipping the order of it. So let's look at this to get that example. So let's say we have an input-output table with constant differences. It will always match some linear function, and the slope of the line is whatever that constant difference is. This, on the other hand, theorem 1.2 says, if we have a linear function, so you notice this says if we have a table with constant differences, then it must match a linear function, right? The other one's just being reversed. So here's table, linear function. We're flipping it. If I have a linear function, it must have a constant difference table. So basically, these could kind of be smashed into one, but it's not always true that if you reverse it, that it still is still works, right? But it does for this, okay? So if we knew we had some linear function, and remember this is one common form of linear functions, this a here is our slope, and this here is our y-intercept of the line. So if it's a linear function, then it must have differences which are constant. There's a really cool way we can prove this, and it will not take a whole lot of time. So this may not be the most exhaustive proof of this, but it works out pretty well. So let's say we have x as my input and ax plus b as my output. Well, when x is 0, meaning let's just plug in 0 for x here, a times 0 is 0, right? So this only leaves me with b. And that again reminds us that this is the y-intercept. You remember on a graph, the y-intercept is wherever it crosses the y-axis. But if you're going to cross the y-axis, that always exists whenever x equals 0. So 0b. This is already showing us why that works. And when x is 1, well, when x is 1, it's a times 1 plus b. So it's just a plus b. And then when it's 2, it's 2a plus b. And when we get 3, it's 3a plus b. Right? So again, all I really did was plug in these various numbers, right, for x here. And then the output I get looks like this. Well, remember, right now what we're kind of trying to do is realize the connection between a linear function, right? So remember, this is automatically linear. That whole thing. We know that is going to be a linear function because we've learned that in the past. The cool thing is what we're trying to connect it with here is, are the differences really constant? Well, if I go from here to here, how much did I increase? Well, this has a b. The only thing I added was an a, right? So there we go. b plus a gives me a plus b, right? Well, from a plus b, how did I get to 2a plus b? What's the only thing that was added on to here? Another a, right? So this is also a. Well, again from here, these b's, there's no more b's adding on. The only thing we're doing is just adding another copy of a. So it turns out we can see that this is just generating the same difference the whole way down. And I'm sure you'd be convinced that this works just continuing on further and further, right? Because it would be 4a plus b, 5a plus b, etc. And then this would just continue to be constant, and a would be what it is. And the cool thing is, if you remember, like we said in the theorem there, this is always the slope. And since we figured out that's the same as that constant difference, then pretty much we've proven that rule. So, anyway, there's a nice conclusion to the lessons we've been doing lately, and that's a really important one. And I hope you guys have a good day. Happy math, and we will see you next lesson.